Okay, so here I'm going to be going over some example FRQs for the rotational motion test. So let's get started. Here we have an amusement park ride in which a cylindrically shaped chamber spins around a central axis. People sit in seats facing the axis, their backs against the outer wall. At one instant, the outer wall moves at a speed of 3.2 meters per second. And if the cylinder has a radius of 2 meters, what force would an 83 kilogram person feel? All right, so for this problem, what you're going to do is you're going to be using the equation for the centripetal force. So we know that the centripetal force, Fc, equals mv squared over r. And if we want to understand what's going on, so here we have the cylinder, and let's imagine that someone's back is against the wall, okay? And the cylinder is going to be rotating around the circle. The forces that this person is going to experience is a gravitational force going down, a normal force that's actually pressing against the back of the person. That's going to be the normal force. And the force that actually holds them up is the static frictional force. Okay, because if there's a normal force and there's a coefficient of friction, there has to be static friction. And the idea is that as the wheel rotates, the normal force is going to be providing the centripetal force. And as long as the wheel is rotating fast enough, the static frictional force is going to hold up their weight. Now for this problem, all we need to do is just plug and chug, because we have the mass of the individual, we have the speed, we have the radius. So here we have 83 kilograms. V is 3.2 meters per second. And we know that we have to square it, and the radius is 2 meters. Okay, and if you plug all that into your calculator, what you should get is about 425 newtons. Okay, so that one's an easy one. You just have to use the equation for centripetal force, and conceptually, it's helpful to know that the normal force is what's providing the centripetal force in this situation. Okay, so next problem. Here we have a CPU fan that has a diameter of 120 millimeters. If it spins at a rate of 2,000 revolutions per minute, what is the centripetal acceleration experienced at the edge of the fan blades? So with this problem, it's important to remember that you have to do conversions, okay? So in terms of the equation that we're going to use, there's actually two equations for centripetal acceleration. So there's the v squared over r. But the one that's going to be better to use for this example is actually omega squared r. Now, to understand why these two are the same, we understand that the relationship between the tangential velocity and the angular velocity is just a factor of r, right? So omega times r. So in other words, if I have a fan, right, let's just imagine, right, these are the fan blades, okay? At the very tip of the fan blade, there's going to be a tangential velocity, and it's going to be rotating at a certain rate, okay? And the relationship between that tangential velocity and the angular velocity, omega, is based on a factor of r, right? So omega times r, that tells you the tangential velocity. So that you're going to want to use this expression. So, just based on the fact that we're dealing with angular velocity, we can just use omega squared r. So now let's figure out how to do the conversions. So something that's important to note, this is talking about the diameter of the circle, not the radius, right? So you have to understand the diameter is the end-to-end distance, and the radius is half of that, right? So radius is equal to 1/2 the diameter. Okay, so that's 1/2 of 120 millimeters, right? So we have 60 millimeters. But we're going to need to convert this to meters, which is the SI base unit. So something you need to note is that there are 1,000 millimeters in 1 meter, right? That's what the SI prefix milli means. It means 1/1000th. So I'm just going to divide this 60 millimeters by 1,000. So I know it's going to equal 0.06 meters, okay? So that's our radius that we're dealing with. Now we're going to have to convert from revolutions per minute to radians per second, all right? Now this one I'm going to write it out using dimensional analysis and show all the ratios. So let me write this all out. So I have 2,000. This is omega we're dealing with. So 2,000 revolutions per minute. Okay, so revolutions per minute. All right, and now we got to convert. So let's convert the revolutions to radians. So what I'm going to need to do is put revolutions in the denominator. And I know that the relationship between revolutions and radians is that for every 1 revolution, there are 2 pi radians. All right, so a full circle is 2 pi radians. And obviously, if you go around the circle once, that's a revolution. So this is the conversion factor. And then the other conversion factor, we have to go from minutes to seconds. Now, keep in mind, minutes here is in the denominator. So I'm going to need to put minutes up here in the numerator when I'm converting. And I need seconds. All right, so I know that for every 1 minute, there are 60 seconds. All right, so when you do all the math, what you're going to end up with in terms of the angular velocity, you should end up with about 2.09 rads per second. All right, so that is the, oh wait, not 2.09, what am I saying? I misread that. Yeah, because we're dealing with 2,000 revolutions per minute. All right, so it's about 209. So about 209 radians per second. All right, so now I have my angular velocity, I have my radius, and now I can calculate the centripetal acceleration. So I know it's omega squared r. I'll just write that out again. I have 209 rads per second, and I'm going to square it and then multiply by the radius, which is 0.06 meters. And when you actually perform the calculation, what you end up with is about 2,600. So 2,630 meters per second squared. Now, if that seems like a large number, that's because it is. And that kind of just shows you just how fast a CPU fan actually spins. I believe when they design the fans, they have to actually account for the fact that the fans are going to stretch a little bit. So because they're spinning so fast and the G-forces that the fan blades experience, they have to actually be pretty precisely manufactured to account for the fact the fans are going to actually bulge out a little bit from all that centripetal acceleration they're experiencing. And we got to make sure it doesn't wobble, right? Because if it has any sort of wobble to it, then the fan would kind of rip itself apart. So yeah, 2,630 meters per second squared. I would say the most important thing with this problem is making sure that you know how to do the conversions. So converting from revolutions to radians, minutes to seconds, from millimeters to meters. Also understanding that we're dealing with the diameter, right? So it tells you the diameter, not the radius. So just really reading the problem and making sure that you know how to do all the necessary conversions. So next one, let's go into here. So we have a car that has tires with the coefficient of static friction of 0.5. It enters an unbanked turn that has a radius of 30 meters. What is the maximum speed the car can safely negotiate the turn? So something that's important, this is an unbanked turn. All right, so it's flat. So it's just turning on a flat road. And we need to figure out the maximum speed. All right, we know the radius is 30 meters and the coefficient of friction is 0.5. Now to understand how to set up this problem, all right, so let's imagine we have the car here. Here's the road, and it's going to take a turn. Okay, so it's going to take a turn like that. When you're drawing the free body diagram, we know there's going to be a centripetal force that has to act on the car because that's what it needs in order to actually make the turn. If there was no centripetal force or if there was no static friction, the car would just slide in a straight line. It would not be able to make the turn. So using a free body diagram, we understand that the force that's going down is the force of gravity. It's being held up by the normal force. And the force that actually provides the centripetal force is going to be static friction in this case. So in terms of setting up the equations, first I'm going to write down the equation for centripetal force. I know I'm dealing with mv squared over r. All right, and now I need to find the static frictional force. So I know the static frictional force is what provides the centripetal force. Now to find the static frictional force, I need to remember that the force of friction, remember the fun equation, okay? So friction is equal to coefficient of friction times the normal force. And the normal force in this problem, right, this car is not accelerating up or down. The only acceleration is from the centripetal acceleration. So that being said, I know normal force has to equal gravity. So in this case, normal force has to equal gravity, right? That's just going to be m times g. All right. Now I'm going to put all these expressions together. So solving for static frictional force, I know that's equal to mu times mg. All right. And now I'm going to set this mu mg equal to the centripetal force. All right. So let me make some space here. So I have mv squared over r is equal to mu times mg. The m's are going to cancel. Let me see, can I use a different color? Yeah. So the m's are going to cancel out. All right. And then what we end up with is v squared over r equals mu times g. And for this problem, we're trying to figure out what v is, right? So it's asking what the maximum speed that it can actually make the turn. So think of it like the speed limit that they post. So let's see, I'm going to take the radius, I'm going to move it to the other side of the expression. So I have mu times g times r. I'm going to take the square root of both sides. So square root of mu g r. And then let's actually plug in the numbers. So I'm to have a static friction, coefficient of static friction of 0.5. The acceleration due to gravity on Earth is 9.8. That's what g is. And then r, what was the radius? Let's see, 30 meters. All right, so I'll do 30 meters here. And when I plugged all that into my calculator, I got about 12.1 meters per second. All right, so that's how you do that problem. This is for unbanked curves, right? It's pretty much set up the same way every time. So then finally, we have a problem using Newton's law of universal gravitation. So here we have two students, they're sitting 2.5 meters apart. If one student has a mass of 50 kilograms and the other has a mass of 60 kilograms, what is the gravitational force of attraction between the two students? So this one, you're going to use Newton's law of gravitation. So G m1 m2 over r squared. And we have these two students. They're going to feel this force of gravity. Not actually, though, because we're going to see it's a very, very, very small number. But technically, there is a force of gravity between them. So let's just write out all the values. So big G is the constant for universal gravitation. So it's 6.673 times 10 to the negative 11. I'm not going to bother putting the units. Technically, the new units are Newton meter squared per kilogram squared, but you don't have to worry about that. We just know the value is 6.673 times 10 to the negative 11. Let's see, we got 50 kilograms. We got 60 kilograms. And that's the product of the masses, and we have to divide it by the radius squared. So this r, this is actually the distance between, actually I like to use big R. This is the distance between the masses. So if I have mass 1 and mass 2, okay, the distance between them, I like to use capital R for that. And the reason why is because basically we're going to see that in a lot of cases when we're looking at universal gravitation, we're going to be talking about orbits a lot of the time. So, right, so let's imagine we have the Earth and we have the Moon, and the Moon orbits the Earth. Okay, and let's see, we have this distance between the Earth and the Moon, right? It's only natural to use R, right? Because we know the Moon's going to go around the Earth once a month. Now, there's not going to be any problems on that, at least not any free response problems that are dealing with that. But in terms of being able to use Newton's law of gravity, we do need to be able to do this. So here we have 2.5 meters. And the thing to look out for in this problem is to make sure you type it in your calculator correctly, right? So the most common mistake with using Newton's law of gravity is just typing it in incorrectly. All right, so be careful, double check your work. I would recommend doing this calculation twice just to be sure. But you know, when I ran it through my calculator, I ended up with a value of about 3.2 times 10 to the negative 8 newtons. All right, so that's how you solve that one. And if you notice, you know, these problems aren't particularly difficult. So we did a very similar problem to this one on the gravitation classwork. Unbanked turns, we did a very similar problem when we were talking about banked versus unbanked turns. Here, and this is all like from the beginning when we were doing rotational motion and centripetal force. So both of these had to do with centripetal force. So I don't remember the exact days of these class kicks. Let me check. Yeah, so you can do you can review day 8, day 5, what was the other one? And day 6. So day 5, day 6, day 8, those are other problems that are similar to these, but basically, this is what you need to be prepared for the test. And that's pretty much it. If you have any questions, feel free to email me. If you want to review any additional content, we can do that after school. But I'm confident if you know how to do these problems and you've followed along, you should be fine for the test.